for our next talk, we'll have Pierre BOTTERON, who will speak about graph games and communication complexity.
Yes, thank you for the introduction. Good afternoon, everyone. So I'm pleased to talk about graph games and communication complexity. It's a joint work with Moritz Weber, who made a talk on Tuesday. The motivation behind this work comes from this observation. The principle of communication complexity has interesting consequences to the CHSH game. So what could be a good consequence to graph games? So we will see some connections between graph games and communication complexity. And we will see two games, the graph isomorphism game and the vertex distance game. But before beginning, I just want to define a very basic notion, which is the Pierre box. A Pierre box is simply a black box with two inputs and two outputs. Alice has access on the left part, Bob has access on the right part. There is no communication, no signal between the two parts. And this box always satisfies this condition that the sum of the outputs mod 2 is equal to the product of the input. So please remember this definition because we'll need it throughout the talk. So let's go in the graph isomorphism game, which I recall the definition. I just present a simplified version of the game. So imagine you have a graph G. Alice and Bob receive some vertices, GA and GB from the graph. They need to answer some vertices from another graph, H, and we say that they win the game if and only if they satisfy the three rules here. So if they had the same input in the graph G, they need to answer the same input. If they had adjacent vertices, they need to answer adjacent vertices in the graph H. And if they had non-adjacent and non-equal vertices, they need to answer with non-adjacent and non-vertices in the graph H. What I claim is that from a perfect strategy to this game, we can generate a Pierre box. So remember the black box from before, we can generate it from a perfect strategy to this game. How do you prove it? It's a very easy proof. So you just pick some x and y, some bits, and you want to produce a and b such that the sum mod 2 of a and b is equal to x times y. So we will build a protocol using the perfect strategy at the graph game. Imagine Alice receives x equals 0. Then she will choose this vertex for the input of the graph isomorphism game. Otherwise, she will choose this one. And for Bob, depending on y, he will choose these two vertices. So then they play to the graph isomorphism game using these vertices. They obtain some outputs from the graph H. And from the outputs, they will define A and B according to which triangle they get the output. So 0 for the first one, 1 for the second one, and the same for both. So I claim that with this protocol, you can generate the Pierre box. So we just need to check that this formula holds in any case. We have 4 cases to check. The case x equals 0 and y equals 0. In this case, we have the same input vertex in the graph G. So as they have a perfect strategy, we know that they will have the same outputs. So the two outputs will be in the same triangle, either the top one or the bottom one. But you can see that in both cases, you have that a plus b is equal to 0 mod 2. You have 0 plus 0 or 1 plus 1, which is equal to x times y in this case. So the first case, we satisfy this equation. If we take a different example, x equals 1 and y equals 0, we have adjacent vertices in the input graph. So in the output graph, we will have adjacent vertices because they have a perfect strategy, so they must satisfy the second implication. And therefore, again as before, they will have outputs in the same triangle, so the sum of a and b will be equal to 0 mod 2, and they will satisfy that it's equal to the product x times y. So in the second case, it's valid as well. It's the same proof if you take x equals 0 and y equals 1. You have adjacent vertices here. The last case that remains to be shown is the case x equals 1 and y equals 1. You have non-equal and non-adjacent vertices in the input graph. So in the output graph, you will have non-adjacent and non-equal vertices, which is equivalent to saying that they will have vertices in two different triangles. So you have two possible configurations. But in both cases, you will have that a plus b is equal to 1, which is good because x times y in this case is equal to 1 as well. So in both cases, you have that a plus b mod 2 is equal to x times y, which is precisely the definition of the Pierre box. So now you might say, yeah, it works only for this example of graph. It's a very specific example of graph, but actually no, we have generalizations. So a first easy generalization is this one. If the graph G has diameter bigger than or equal to 2, and if H is the union of two complete graphs, then from any perfect strategy for the isomorphism game, one can generate the Pierre box. So it's a first generalization. We have another example of generalization. If you have two graphs that are non-signaling isomorphic with diameter bigger than or equal to 2, and this time you take H not connected, so it's a weaker condition than before. You just want to have several connected components, maybe not complete. You assume some symmetry in a common equitable partition. So I don't have time to recall the definition of common equitable partition, but you just want to have some symmetry. And then there exists a perfect strategy for the game that generates a Pierre box. Okay? I just wanted to give a last example of theorems that you can get. If you have two graphs like in theorem 2, if you assume moreover that H is strongly transitive and D regular, then every perfect strategy, so the difference between theorem 2 and theorem 3 is that in theorem 2 is that there exists a perfect strategy, and in the last one, every perfect strategy for the isomorphism game generates a Pierre box.
So yes. By perfect strategy, you need a perfect non-signaling strategy, right? It cannot be a quantum strategy.
As a consequence, it cannot be quantum, because otherwise we couldn't be able to generate the Pierre box. But I didn't assume that it's not quantum. It just needs to be non-signaling, but it might be.
But you see that the graphs are not quantumized, right?
Yeah. So in both cases, we generate a Pierre box. Why is it so interesting to generate a Pierre box? It's because of the next slide, because the Pierre box collapses communication complexity. And this will be the link between graph games and communication complexity. What is communication complexity? I want to explain it using a game. You have two players, Alice and Bob. They don't communicate, and they want to compute a function f, Boolean function, with strings as input and a bit as output. Alice is given f and the first string input, and Bob is given f and the second string input. Alice wants to answer a bit a, such that a is equal to the evaluation of the function. So it's not so easy to win the game, because Alice knows only half of the inputs. We allow Bob to send one bit of communication to Alice, but no more. And it's quite a small amount, because he receives n bits, and he can send at most one bit. And then they can as well use a non-local box, like the Pierre box that I introduced before. So this is the setting, and we say that the non-local box in blue collapses communication complexity if there exists a constant q, such that for any n as large as we want, and any function with input size 2n, and any strings, Alice correctly guesses the value of f with probability bigger than q, where q does not depend on n and f. The collapse of communication complexity is very surprising, because it means with high probability, Alice is able to compute the function distantly with Bob with only one bit of communication, no matter how complex the function is. So, because the number of communication bits does not depend on n. And so the fact that we use is that the Pierre box collapses communication complexity. So if we put the Pierre box here, then we have the collapse of communication complexity. And as a consequence, from the previous theorems, as we were able to generate the Pierre box, we know that the perfect strategies presented in theorems 1, 2, 3 from before, they collapse communication complexity. So it's the first connection between graph games and communication complexity. Now I want to talk about another game, the vertex distance game. I need to introduce to define it. So it's the same kind of setup. We have Alice and Bob receive vertices from a graph G. They need to answer vertices from another graph H. And this time the rule of the game is slightly different. They need to preserve the distance of the vertices. So the distance of the output vertices must be the same as the distance as the input vertices if it was smaller than a parameter d. So we fixed the parameter d. I didn't write it at the beginning, but I should have. And otherwise, if it was a large distance at the beginning, it should be a large distance at the end. If they have a perfect strategy for this game, we say that G and H are d-isomorphic for the distance big D. You can see that we have this chain of implications. If we have a strategy that preserves all the distances until 2, then we can preserve all the distances until 1 and all the distances until 0. And we have some interesting particular cases. If you take the case d equals 0, it's exactly the definition of the graph bisynchronous game, because in the case d equals 0, you want to preserve equality in the first line, and you want to preserve non-equality in the second line. So if you have two equal inputs, you want to have two equal outputs, two different inputs, you want to have two different outputs. If you take d equals 1, you exactly recover the graph isomorphism game, because the distance 0 corresponds to equality, distance 1 corresponds to adjacency that you want to preserve, and distance, large distance corresponds to non-equality and non-adjacency. I don't want to spend time on the last case, so I'll skip it. If you want to characterize the perfect quantum and classical strategies to this game, it's a very, it might not be surprising to you, but it was surprising for us, is that you recover exactly the same perfect strategy as for the graph isomorphism game. So we have these two theorems. Here, G and H are d-isomorphic, meaning that there exists a perfect strategy for the d-distance game. It's equivalent to having a perfect strategy for the graph isomorphism game in the classical sense, and the same as well holds for the quantum strategies. And as we had characterization for the graph isomorphism game, these three characterizations, they characterize as well the one for the distance game, the same here. But we'll see that it's not the case for non-signaling strategies. We'll have a different behavior. So let's characterize non-signaling strategies. I first want to recall the characterization in the graph isomorphism game. We say that two graphs are fractionally isomorphic if there exists a bistochastic matrix P, such that we have this relation between the adjacency matrices. And so we have this famous characterization that the two graphs admit a perfect non-signaling strategy at the graph isomorphism game, if and only if they are fractionally isomorphic, if and only if they admit a common equitable partition. Okay. So we have a generalization of this characterization for the distance game. And to have this generalization, we need to introduce a generalization of this fractional isomorphism. So we have the d-fractional isomorphism defined as the existence of a bistochastic matrix P, such that we have this relation. And now it's no longer the adjacency matrix, but it's the matrix with coefficient 1 for every vertex at distance exactly t. So it's a kind of generalization of the adjacency matrix. Adjacency matrix corresponds to t equals 1. And so we get this theorem, this characterization of perfect strategies for the d-distance game. So they are non-signaling isomorphic if and only if they are d-fractionally isomorphic, if and only if there exists a d-common equitable partition, which is as well a generalization of the classical common equitable partition definition. Okay, and what I said before is that this characterization is not the same as this one. And we have an example. If you take this big cycle, so containing 2 times 2d plus 1 vertices, it will be d-isomorphic to the union of these two cycles, but not d plus 1 isomorphic. So it's a sequence of graphs that satisfy this thing. And in particular, if you take d equals 1, which corresponds to the graph isomorphism game, you have two graphs that are isomorphic for the graph isomorphism game, but not distance 2 isomorphic for the distance game. So the perfect strategies for the two games are not the same, as opposed to classical and quantum ones. As a consequence, we have a chain of implications. So I said before that having a perfect, a classical isomorphism between the graph is equivalent to having to preserve all the distances in the distance game. If you have such an isomorphism, it implies to having quantum isomorphism, but the converse is false. And it's equivalent to having to preserve the distance d for any distance. It implies that you are fractionally isomorphic for any d, but we don't know if the converse is true or not true, so this question is left open. And by definition, so we can go from the left to the right easily from the observation that if you preserve all the distances, then you preserve distance d0 plus 1, then you preserve distance d0, and then you preserve distance 1. And from this counter example, we have that all these implications from the right to the left are false. So it only remains to prove this one. And yeah, I wanted to mention applications to communication complexity. So here are two examples of theorems. If you satisfy this condition of the diameters of the graph, and if H admits exactly two connected components, then for any perfect strategy, a perfect non-signaling strategy at the d-distance game, we have a collapse of communication complexity. Another example of a theorem like this is that if you have two non-signaling isomorphic graphs and a condition on the diameter of G, and H is not connected, and if you have as well some symmetry, then there exists a perfect strategy at the distance game such that you have a collapse of communication complexity. So this is another connection between graph games and communication complexity. And just to go to the conclusion of this talk, I want to present two open questions from this work. The first one that I mentioned before, from the strict implications. Is it possible to find two graphs, G and H, that are d-fractionally isomorphic for any distance d, but not quantum isomorphic? And the other question is a Lovász type characterization. You know that you can characterize isomorphism using homomorphism counting. For example, in the classical case, you just need to count homomorphism from any graphs. In the quantum case, you need to count homomorphism from planar graphs. In the non-signaling case, you need to count homomorphism from trees. So what could be the good family of graphs here to have the equivalence between this new notion of isomorphism and the homomorphism countings? And that being said, I want to stop here. Thank you.
So again, we have time for one or two questions, I think.
If you take your graph and you define a new graph, say 2 versus are adjacent the distance at most d, then is this vertex distance game the same as the graph isomorphism game for these graphs?
So you take adjacent vertices if they are at most a distance t.
Yeah.
So we have a characterization like this. I don't know if it's at most or exactly distance t, but we have something like this in the paper. Yeah.
I see. And maybe a good candidate, maybe this might be equivalent to some linear programming or STP relaxations of graph isomorphism, like some level of Sherradi-Adams or some level of Lassay. So might be
Maybe.
a
But,
good
yeah.
thing to look into.
We can talk about it if you want. Yes?
Often if you take perfect non-signaling and you let the number of players increase, then perfect strategies converge to perfect classical strategies if there's a large enough number of players. Have you looked at any of these games for more than 2 players?
Not yet, because communication complexity is usually defined in 2 players game. When you want to define it for 3 players, it's slightly subtle. So not yet, but it's a good direction. Yeah.
For graph coloring, graph homomorphism.
So the question is that can you generate the PR box from a multiplayer game?
No, the game, just the game.
Just the game.
Yeah. take the use non-signaling strategies but multiple players.
So the question is that does it tend to classical?
It does for some games.
So we don't know. It's a good question.
Okay, since time is tight, we better save the rest of the questions for the break. So let's thank our speaker again.